Okay, question 8. An experiment, exciting, sciencey, involves two substances, substance 1 and substance 2, they're the chemical names for them, whose masses are changing. The mass M1 and the mass M1 grams of substance 1 at time t is given by that. The mass of substance 2 is given by this table. At a critical stage in the experiment is reached at time t hours, when the masses of the two substances are equal. Very exciting. This is how they made the Hulk. Right. So find the rate at which the mass of substance 1 is decreasing when t is 10. As soon as we see this bit, the rate at which, that tells us it's a differentiation thing, isn't it? Rate of change is all about differentiating. So we've got that M1 is 400 e to the minus 0.014t. When we read that says find the rate, that means we need to differentiate. Okay? And it's when time equals something, so it's the rate of change with respect to time. So dm1 by dt. Now this is, again, it's a little bit of a function stuff. It's the function e to the something, but the something's quite simple. So that's the derivative of the whole thing, Big Bear, as it were, is 400 e to the minus 0.014t times the derivative of the little bit, which is 0.014t. So we're timesing by minus 0.014. And if we tidy this up, then we've got 400 times that, which gives us, I think, minus 5.6, is that right? Minus 5.6 e to the minus 0.014t. And the question said, when t equals 10, and it wants the answer correct to two significant figures. So if t equals 10, we put 10 into that expression, and dm1 by dt is that would be minus 5.6 e to the minus 0.14. Minus 4.868. But of course the question said give it to two significant figures, so therefore minus 4.9. What are we? Grams per hour. Oh, hang on. I may have just done something slightly wrong in here. What have I done slightly wrong?
Then it said it's decreasing, so it should have a minus on it.
That's it, yeah. It said find the rate at which the mass is decreasing. So the fact that I got a minus answer tells me it's decreasing, but if I'm expressing the rate at which it's decreasing, then it would be nicer to write it.
Would you raise math for this in minus?
I'm not sure, I can't remember what the mark scheme said for this one. I would say potentially, because I think they could take a mark up for that. We'll check the mark scheme later on and see. Part 2. Show that t is the root of an equation of the form e to the kt equals c, where the values of the constants k and c are to be stated. Well, remember, what was t? What was t all about? T was the point at which the masses of the two substances were equal. Well, we haven't got an equation for this one, so we're going to need to find an equation for that one. What we did have there, well, we've got here it's increasing exponentially. So we need to know it fits this exponential growth. So M2, as soon as we read it's increasing exponentially, we know that M2 is something times e to the something times t. I'm using k, which they also used, so that could be a problem, but anyway, we'll just go with it. And what I know about this is that when t equals 0, my expression has n2 as being 75. So if I sub in those values, I get 75 is a e to the 0. In other words, 75 is equal to a. So that's a good start point. I also know that when t is 10, m2 is 120. Just as an example up there. We've also got when t is 20, m2 is 192. So let's sub that in. That means that 120 is 75. That's what a is. E to the 10k. So I'm going to rearrange this to find out my value of k. So 120 over 75 is 1.6. I would like to know what k is. So natural log of 1.6 is 10k. So k is 1/10 the natural log of 1.6. A particularly nice thing to have found, but that's where we're up to. Now t is the time when the masses are the same. M1 equals M2. And so M1 was 400e to the minus 0.14t. 400e to the minus 0.14. And it's big T, pointed at the same. And M2 is 75 e to the k, which I found as being 1/10 natural log of 1.6 times big T. It's horrible, isn't it? I need to find the value of T at this point. But I need to show that this is the root. Well, yeah, I need to get it so it says e to the kt equals c. And find the solution of that, or find the values of k and c from that equation. So I need to rearrange this so I've got the e bits on their own. Well, let's just try and tidy it up a little bit. I've got 75 and 400, so if I divide through by 75 again, I get 400 over 75, which is 16 over 3. I want to get the terms involving e all together. So this isn't a particularly neat way of doing this, but what we'll do is we'll divide through. Okay. Now we remember how indices work. Going right back to core 1, and we know that here we would subtract the powers, wouldn't we? So actually, we've got that term, 1/10 ln 1.6t, take away that one, minus 0.014t. And I'm not sure how exact we need to get our value of k. Given that it wasn't exact in the first bit, I think it's probably right just to do it with a few significant figures. If we do 1/10 ln 1.6 minus 0.014, so plus 0.014, then that should give us some kind of value, and I've got it to come out as being 0.061. As being the solution there. In other words, what we're saying is that C equals 16 over 3 and K is 0.061. And that took a little bit of doing, didn't it? It was a little bit messy to get to that point. Then, finally the question said, hence find the value of t correct to 3 significant figures. Well, actually, we've done all the hard work for this. Having got to this point here, we now just need to find the value of t that satisfies that, which is how do we solve this kind of equation where the unknown is in the power? Well, we take logs of both sides, don't we? We rearrange this to say that the natural log of 16 over 3 is 0.061t. I was probably, just to be on the safe side, having got that full figure on my screen, which was a lot longer than that, I would have stored it in my calculator memory. I would have then divided the value of ln 16 over 3 by that stored calculator memory figure. And we get, well, I got that t was 27.4 hours. Just three significant figures. And there we go. And that's maths.